everyone, welcome to the fourth day of my YouTube video series. What if I told you that fastest algorithm isn't always the best algorithm? Today we are diving into space complexity, the often overlooked twin time complexity that can make or break your application into real world. By the end of this video, you will know exactly how much memory your code is consuming and why it's matter. So, what does space complexity mean? Space complexity measures the total amount of memory space an algorithm needs to execute completely, just like time complexity. It tells us how fast our code runs. But space complexity tells us how much memory our code consumes. Think of your computer's memory like a parking lot. Each variable, data structure or function cell needs a parking spot. Space complexity tells us how many parking spots our algorithm need as our output grows. The formula is space complexity equal to input space plus auxiliary space. We will break this down shortly, but remember, we are measuring memory consumptions as function of input size. Let's discuss the difference between time and space complexity. Now you might thinking, isn't this just like time complexity? Not quite. Let me show the key differences. Think about time complexity. It measures number of operations and concern with how long the algorithm takes, and it questioning how does runtime grow with input size. But space complexity is different. It measures amount of memory used and concern with how much RAM the algorithm needs, and questioning about how does memory usage grow with input size. Now I will explain why space complexity matters. You might ask, with modern computers having gigabyte of RAM, why should we care about space complexity? Here why it's crucial. First one is embedded system and IoT devices. Smartwatch, fitness tracker or IoT sensor has limited memory, sometimes just kilobytes. So space efficient algorithms are essential. Second one is mobile applications. Memory hungry apps drain batteries and get killed by the OS. Users hate the app that slow down their phones. So that's another issue. Before we dive deeper, let's understand memory actually get used in programs. First one is stack memory. You can see the visual here. So stacks store local variable, function parameters, return addresses and function call information. So characteristics are, it has fixed size, usually 1 to 8 MB, and fast access, automatic cleanup when function returns, LIFO structured, that will last in first out. And the second one is heap memory. The heap stores dynamically allocated objects, data structures, array, list, trees, objects created at runtime, and the characteristics are flexible size, uses available RAM, slow access than stack, manual or garbage collector cleanup, can fragment it over time. Third one is code space. It stores compile, program instructions, constant and literals, usually read only, and static or we call global space. It stores global variables, static variables, constant that live for program's lifetime. So that's it. You can see here memory layout visualization. I will show you it for the better understanding. Let's discuss input space versus auxiliary space. This is crucial for understanding space complexity calculation. So, the input space memory required to store the input data itself. If the input is an array of n element, input space equal to O(n). So, auxiliary space explore temporary space used by the algorithm, not including the input space. Auxiliary space equal to O1 minus just the total variable. When we say space complexity, we typically mean total space equal input plus auxiliary space. However, main algorithm problem asks specifically for auxiliary space minus extra space beyond the input. Big O notation for space complexity. Just like time complexity, we use big O notation for space complexity. The same rules apply. We focus on the worst case, we drop constants, we keep the dominant term. So let's look at the example. Constant space. No matter the input size, we always use the same amount of extra memory. Here you can see the code lines explain the constant space. There is Python code. Def, that means a function. Sub, a and b are the parameters. Temp a, that means only one extra variable. A assigned to b and b assigned to temp. Okay, then linear space. Memory grows linear with the input size. There's a function create copy array and return the array. Copy size of n. Space complexity in recursive algorithm. Recursion is where space complexity becomes really interesting and tricky. So let's look at this. The call stack. Every recursive call adds a frame to the call stack. We calling factorial 5 and then stack grows factorial 5, factorial 4, factorial 3, factorial 2 and factorial 1. The base case reach factorial 1. So let's move on to the linear recursion example. So recursion depth is n and each frame stores parameter plus local variable and space constant for call stack. And binary recursion example. Here's the visual of Fibonacci recursion tree. You can see here clearly. Tree has 2 to the power n nodes total, but max stack depth equal to n. Leftmost path. Space for stack, constant for stack, not O to the power n, because we don't store the entire tree simultaneously. Let's analyze the space requirement of common data structures. Arrays, linked list, stack and queues, hash table, dictionaries, binary tree, graphs. Here's the comparison table, data structure, space complexity, and nodes for refer. Analyze the space complexity step-by-step method. So, step 1, identify variables, count all variables and their sizes. And step 2 is identify data structures, arrays, lists, dictionaries, and note their sizes. And step 3 is analyze recursion, check recursion depth call stack in the call stack. Step 4, adopt space, sum all space usage. And step 5 is express in big O notation, keep dominant term, drop the constants. Let's solve real problem step by step. Most people try to solve this by picking a number and then searching rest of the list for its partner. That's slow. This code uses a hash map, the same dictionary, to remember numbers it passes them. Instead for looking for a partner, this code looks backward at its memory to see if the missing piece has already been found. So let's go to line by line breakdown. This is toSum problem. We have created function called toSum and parameters are nums and the target. This is a Python code and you can see here scene equal and curly bracket open and close. This we create an empty dictionary and it will store value and this index. So here for I num in enumerate nums. This we loop through the list. I is the current position and num is the value at that position. So here complement equal target minus num. The math if our target is 10 and the current number is 7, the complement is 3. Now effectively looking for a tree. If complement is seen, return scene complement I. We check out dictionary. Did we see a tree earlier? If yes, we found the pair. We return index of the tree which we stored earlier and the current index I. Say num equal I. If we didn't find the partner yet, we put the current number into our memory so that a number later in list we can potentially match with it. We'll explain why this is better. If we use toLoop to compare every number, it would be slow. By using scene dictionary, we only pass through the list one time. So this code has the features speed, effort and trade-off. Think of like this. You walk to a room and calculate who your perfect math partner would be. You check a guest list at the door to see if they arrived before you. If they are, there you done. If not, you add your name to the guest list and wait for someone else to find you. Let's recap what we have learned today. Space complexity measures memory usage as input rows, and stack and heap are the primary memory areas we analyze. Auxiliary space is the extra space beyond the input, and recursion uses stack space equal to its depth, and trade-offs exist between time and space complexity. Here are practical tips. Always consider both time and the space complexity. Use in place operation when possible. Be aware of recursion depth. Hash tables are powerful, but use ON space, that is constant space. If you find this video valuable, please click on the like button and subscribe our channel. See you in the next video. Until then, happy learning.